All right, let's take a look at an example of a t-test. Okay, a t-test is used for testing a claim about a mean when sigma is unknown. Okay, so let's take a look at this problem. The Internal Revenue Service claims that the mean wait time for callers during a recent tax filing season was at most 15 minutes. A random sample of 40 callers has a mean wait time of 16.7 minutes and a standard deviation of 2.7 minutes. Is there enough evidence to reject the claim at alpha equal 0.01? Okay, so what we need to do first is we need to write the claim as a mathematical statement in terms of the appropriate parameter. Okay, so the parameter that we're working with in this section is mu. Okay, and if this were all mixed up on a test, this would be your clue that we're dealing with mu, okay, because the claim is about a mean. Okay, so the statement is, or the claim is that the mean wait time for callers was at most 15 minutes. So as a mathematical statement, this is going to be mu less than or equal to 15. Okay, so this is the IRS claim. Okay, so because this contains the case of equality, this is going to be the null hypothesis. Okay, so this by default makes the alternative mu greater than 15. Okay, so this is a single-tailed test. It's going to be an upper-tailed test. Now let's go ahead and find the standardized test statistic. Okay, so it follows the t-distribution, and it's equal to x bar minus mu, the hypothesized mean, over s over the square root of n. Okay, so in the problem, we're given that our sample was 40 callers, and it's equal to 40. Our sample mean from that 40 was 16.7 minutes, and a standard deviation of 2.7. Okay, so now I'm using the notation S because this is based on a sample. Okay, so it says in the problem a random sample of 40 callers has a mean time of 16.7 and a standard deviation of 2.7. So I know that sigma is not given in the problem. Sigma is unknown, so we need to go ahead and use the sample standard deviation in the problem. Okay, so plugging this in by hand, we get 16.7 minus 15 over 2.7 over the square root of 40. Okay, so again, we're looking at the difference between the observed sample mean and the hypothesized mean, and we're standardizing it. Okay, so we're answering the question, is this difference statistically significant? Okay, so putting this into the calculator, (16.7 minus 15 divided by 2.7 divided by the square root of 40. Okay, so our test statistic is about 3.98. Okay, and again, you need to round as you're told to round in the homework in my stat lab. Okay, so in fact, I'll just carry it out one more decimal place. Okay, 3.982. Okay, so now we need to go ahead and find the critical value. I'm only going to have one because this is an upper tail test. Okay, so I want to shade the area, the rejection area. So I want to draw the distribution. So I want to find the critical value. And I need to use the level of significance given. So let's see, what is that? Alpha is 0.01. So I'm going to draw a bell curve because the t-distribution is bell-shaped. It's actually a little bit shorter with heavier tails than the standard normal curve. Okay, but the mean is also 0. Okay, so I'm going to shade 0.01 area in this upper tail. Okay, so now I need to go ahead and find this corresponding critical value. Okay, so I need the degrees of freedom to use the table. The degrees of freedom is equal to n minus 1, so that's going to be equal to 40 minus 1, which is equal to 30. Oops. Sorry, equal to 39. Okay, so looking at the t-distribution, I want to read down to 39 degrees of freedom, okay, along this column. And then I want to read over to the appropriate area in one tail. Okay, so I want to read over to 0.01 in one tail, and then down. Okay, this is a little tricky to read. Okay, so 39 area of 0.01 in one tail. Okay, so I get a critical value of 2.426. Okay. Now, for example, if this were a lower tail test, just for argument's sake, we would be shading a lower tail down here. Okay, like the z-table, the z-distribution, the t-distribution is symmetric. So the table only gives positive values for t. So if you're down here, you can go ahead and find the positive value, then take the opposite. Okay, so this is an upper tail test, so we're good to go here. So right now, I know my decision is to reject the null hypothesis because this test statistic is lying further out in this tail. Okay, so I know my test statistic is above the critical value, therefore I'm going to reject the null. Okay. Now, finding the p-value using the table is tricky, so we're not going to do that part by hand. We're going to go ahead and use the calculator. Since the table only gives a few probabilities across the top, the best we can do is get a range for the p-value. Okay, and it's kind of cumbersome. So what I'm going to do is I'm going to go ahead and use the calculator to get my p-value. Okay, so I'm going to go to Stat, right arrow over to Tests, and then I want to select t-test. Again, same process. I either have the raw data in a column or I have the summary statistics, which is what I have in this case. Okay, so I need to go ahead and change the information. Okay, the value from the hypotheses is 15. My sample mean is 16.7. My standard deviation is 2.7. And my sample size is 40. Okay, so I can go ahead and change the direction of the alternative to a greater than, and then calculate. Okay, so notice that it gives the same test statistic that we got by hand, okay, approximately. Now, the p-value is extremely small. Okay, so remember, you can't write your E as part of the answer. Okay, you need to write this in correct scientific notation. Okay, so what this means is that the p-value is approximately 1.44 times 10 to the negative fourth power. Okay, so if we wanted to write that in non-scientific notation, I would put 3 leading zeros here and then the 144. Okay, so notice this is an extremely small p-value. So in other words, it's not likely to have observed a sample mean of 16.7 by chance alone. Okay, so let's go ahead and compare the p-value to alpha. Okay, our p-value super small. Okay, 0.000144. Our level of significance is 0.01. Okay, so clearly our p-value is less than or equal to our level of significance, so we're going to reject the null, which is what we saw when we looked at where our test statistic lied in relation to the critical value. So in other words, this little area from the test statistic to positive infinity is really, really small. So clearly this area is less than our area determined by the level of significance. So we would have to reject the null in this case. Let's go ahead and find the corresponding confidence interval. Okay, the level of confidence would be 99% since our level of significance is 0.01. So a 99% confidence interval for mu. Okay, again, I can use my calculator for this. Okay, or you're welcome to go back to section 6.2 and do this by hand. Okay, so I'm going to stat, then tests, then I want to scroll down to the t interval. Again, I have summary stats. What's really nice is that it kept the information that I inputted for the hypothesis test, but I do need to change my level of confidence to 0.99. Okay, so calculate. Okay, so looking at our confidence interval limits, they go from about 15.54 up to 17.86. Okay, so let me write that down. Okay, I've got 15.54 up to 17.86. Okay, this is a range of values likely to contain the true parameter. So looking at this confidence interval and going back and looking at the alternative, this confidence interval has values that are definitely above 15. So this confidence interval is supporting the decision to reject the null. Okay? Okay, so next to last thing we want to do is we want to state the conclusion. Okay, so the conclusion is that we're going to reject the null. Okay, now in this case, the null is the claim, and we're rejecting the null, so we're also rejecting the claim. Okay, so in conclusion, there is insufficient evidence to support the claim that the mean wait time is at most 15 minutes. Okay, so I definitely want to rewrite the conclusion in quote-unquote plain English. Okay, last but not least, since we rejected the null, it is possible that a type 1 error may have occurred. Okay, so since the null was rejected, type 1 error, I'm running out of room here, may have occurred. It doesn't mean that it occurred absolutely. Okay? What it means is that it's possible we just happened to get a fluke of a sample and we rejected the null erroneously. Okay, one way to counter that is to repeat the experiment. Okay, replication is a good way to confirm your conclusions. Okay, so I hope that clears up using the t-table and using the t-test.